Good afternoon to all. Am I audible? Just mention yes in the chat box so that I will come to know that my voice is audible to you people. Okay, I'm going to start my session. Today we will discuss rectifiers and power supplies. The first topic is block diagram description of a DC power supply. Okay, block diagram description of a DC power supply. So, if we have a DC regulated power supply, you can even call it as linear power supply. Which is an embedded circuit, and it consists of various blocks. DC power supply, that is embedded circuit, it consists of various blocks. Let us see those blocks. Okay, so our topic is block diagram description of DC power supply. So let us see those blocks. So these are the blocks. So you can see here, I'll take a pen. So I have another diagram. So I thought this is more, this diagram, it is more visible and more bright. So I thought I will show this diagram. So you can see here the first block is step down transformer. Second block is rectifier circuit. Third block is filter circuit. And this fourth block, that is the last block, is regulator circuit. Okay. So in the block diagram of DC power supply, there are 4 blocks. The first one is step down transformer. Next one is rectifier circuit. Next one is filter circuit. And the last one is regulator. Okay, so even if we won't mention this term circuit, it doesn't matter. So here in this block, in these blocks, circuit is mentioned circuit. Simply you can say step down transformer, rectifier, filter and regulator. That's it. So first of all, we'll start with the step down transformer. Before that, let us see what are all the inputs and outputs of these blocks. What do we give as input and what do we give as output to these blocks? If you observe carefully in this block, at the terminals of these blocks, you can see A, B, C, D and E. Okay. So here A, B, C, D, E represents the inputs and outputs of these blocks. So let us see what is A. What is this? A, let us see. A is a sinusoidal input. A is what? It is a sinusoidal input waveform. So we are going to give a sinusoidal input to this transformer. Okay. So when sinusoidal input is given to this step down transformer, okay. So what do you get? You will get B as output. So here A is the input to the step down transformer. B is the output to the step down transformer. So input of a step down transformer is A and output of step down transformer is B. What is B? So B is also a sinusoidal output. Okay, so this sinusoidal output, sinusoidal waveform you can say. So here the step down transformer is used to step down the voltage level. So if you carefully observe these two waveforms, okay, if you observe the waveform A and B waveforms, this A waveform and B waveform, if you carefully observe the magnitude, this is the magnitude of the sinusoidal input, isn't it? So the magnitude has been reduced here. We are stepping down the voltage level. Okay, we are going to step down the voltage level. Okay, so what is we are getting the input is AC to the step down transformer. Output is also AC. Okay, input and output both are alternating quantities. But what happens here is the magnitude of the voltage. Okay, the magnitude. See here, this is the magnitude of output. This is the magnitude peak value of the input. V peak, I can say Vp. Okay, this is also Vp. But this Vp is less than this Vp. So what is happening? The magnitude of the voltage is reducing. Okay, of the transformer. So this is the input of the transformer. This is the output of the this transformer where the voltage level is reduced. Okay, now let us go back to the block. Now, what is B? What did I say? B is the output of step down transformer. And it is also input of this rectifier. Input of rectifier is B. And what is the output of the rectifier? If there is any disturbance or if my voice is not audible, you can mention in the chat box, anyone. Okay, don't post unnecessary messages. Okay, some of you, yesterday's session, I saw some of you are misusing this session and posting unnecessary messages in the chat box. If you post unnecessary messages, I will take the screenshot of those messages and I will take the necessary actions that are to be required. Okay, unnecessarily you have joined the session to listen to the class. Okay, if you don't want, just quit the class. Okay, if you feel that you are gaining nothing from this session, please don't attend this session. Okay, if you are not interested to learn anything, don't attend this session. Okay, so yesterday I took the screenshots of all the messages. Today also I will take the screenshot of all the messages that are being posted in my channel. Okay, don't worry, I will do what I have to do. Okay then, now this is B. B is what? B is the output of step down transformer and it is also the input of rectifier. Output of rectifier is C. So B is the input of the rectifier. So this is what? This is the input of the rectifier now and output of the rectifier is C. See, this is C. So what is the output of the rectifier? This is it. So you can see you are getting pulsating DC output. This is sinusoidal. This is AC. Okay, this is AC input to the rectifier. This is DC, pulsating DC, not pure DC, but it is pulsating DC. Okay, so you are getting pulsating DC from the rectifier. So to the rectifier, input that is given is AC input and output that is obtained is DC pulsating output from the rectifier. Now let's go back to the block. So now this C, what is C? C is the output of pulsating DC is the output of rectifier. So that pulsating DC, which is the output of rectifier, it is given as input to the filter. Okay, so when C is given as input to the filter, you are getting D is the output. So what is C? C is the pulsating DC output that is given as input to the filter. So pulsating DC signal is given as input to the filter and you will get D as the output. What is D? Let us see. This is D. Okay. So if you see here, the C is the input to the filter, which is pulsating DC input. What about D? So the ripples have been removed. Okay, the full half cycle, you can see, full half cycle was there. Purely unidirectional half cycles were there in your uh, input that was given to the filter. But the filter is filtering out the ripples. Okay, so this is the filtered output. To be more specific, I have one more diagram somewhere. I think it is, yeah, this is, if you see this waveform, this is it. In this diagram, you see, this is the output of the filter. So this is the input of the filter. This is the input of the filter, and output of the filter is this. Okay, so we will discuss in detail. This is the output, this red color waveform which I am drawing above this input of the filter. Okay, so it filters out the ripples. Okay, so this is the output of the filter. Okay, this is how the output of the filter will look like. Now let's go back to the block. Now this D, which is the output of the filter, it is the input to the regulator. Okay, D is input to the regulator and E is the final output. Okay, this is the actual output. E is the actual output and A is the actual input. Okay, A is the actual input and E is the actual output. Okay, so D is the input, filtered output. Okay, D is what? D is the filtered output. So that filtered output is given to the regulator. So regulator will produce the actual output. Okay, so let us see those outputs. This is the input to the regulator and this is the final output. Okay, you can see a purely DC output waveform. Okay, so to this regulated power supply, actual input is this sinusoidal input, and at last you will get the purely DC output. Okay, now let us discuss each block one by one. So, or you can see in this wave, in this block diagram, you can see, okay, in this see, you are giving AC input. Okay, AC input is given, it is not shown here. Okay, and you are getting this AC output from the step down transformer whose magnitude is reduced. That AC input is given as input to the AC output of transformer is given as input to the rectifier. Rectifier produces pulsating available volumes. Aye. So rectifier input to the rectifier is AC. Rectifier produces the DC output, pulsating DC, which is not pure DC. So this pulsating DC output of rectifier is given as input to the filter, and filter will filter out the ripples, and this is the output produced by the filter. That output is given as input to the regulator. That regulator will produce a constant DC. Okay, so pure DC output that is given to the load. So whichever load we want to give DC. Okay, to that load this regulator is connected. Okay, if you want you can draw the diagram. I'll give you a minute. As soon as you complete, you just mention C in the chat box. Okay, so the regulated power supply, it is accepting what? It is accepting AC supply as input, and it is producing what? DC output. Okay, so its input is AC and output is DC. So the regulated power supply, its main purpose of using regulated power supply is to maintain the output constant even if input changes. Okay, even if input changes, the output should remain constant. So different blocks of this regulator power supply, as I have already told you. What are those? Transformer, step down transformer, rectifier, filter, and regulator. So let us discuss one by one. Let us start with step down transformer. So you can see here, you can see a step down transformer here. So by looking at the windings, you can say it is a step down transformer. Number of turns on the primary coil, that is input side, are more and compared to the number of turns on the secondary side. So by looking at this, we can say it is a step down transformer. So what this step down transformer will do, it will step down the voltage from AC supply to the required voltage level. So you can see this is our input voltage. So you can see the magnitude of the input voltage, and this is the output voltage of the step down transformer. This is the magnitude of the output voltage. So I have one more image. So this is it. So you can see, so this is the step down transformer, this is the AC supply. So this is the magnitude of your input voltage, and this is the secondary winding, this is the primary winding to which supply is given. So across the secondary winding, the output V out, okay, V out, this is V in. Okay, so this is the waveform of V in waveform. This is the waveform of V out. So if we carefully observe, time period is same. Here it is written capital T, here also it is written capital T. Time period is same, but what has happened? The magnitude has reduced. Okay, the magnitude has reduced by using this step down transformer. Okay, so the transformer turns also. This transformer turns, turns means what? These are the turns. Okay, so depending on how much voltage I want at the output side, the transformer turns of the are adjusted. Okay, so the manufacturer, depending on how much output he wants, depending on the output that is required by the of course by the customer, the manufacturer will decide the number of turns ratio. Okay, the primary and secondary turns ratio, he will decide that, and depending on the number, the turns ratio of the transformer, the output voltage magnitude will change. Okay, now this output, this is given as input to the rectifier. Okay, this is given as input to the rectifier. So what is the rectifier here? This is the rectifier, isn't it? This is the rectifier. So this rectifier, what does it do? It converts the it converts the bidirectional voltage that has been given to it into unidirectional pulsating DC. Okay, it converts bidirectional input waveform into pulsating DC. Okay, so this rectifier is a circuit which uses one or more diodes to convert AC voltage into pulsating DC. So this rectifier, it can use one or more diodes to convert AC into DC. So you can see here in this diagram, this is rectifier circuit. So you can see only one diode is there. Okay, to convert AC into DC. Or you can use another circuit. This is a bridge circuit. You can see approximately 4 diodes are there. So both the circuits whether it is one diode circuit or more than one diode circuit, they are used to convert AC voltage into pulsating DC. So these rectifiers, they can be either half wave rectifiers or full wave rectifiers. So if it is a half wave rectifier, this is the diagram for half wave rectifier. Okay, this is the diagram for half wave rectifier. This half wave rectifier converts AC voltage into unidirectional pulsating DC voltage using only one half of the applied AC voltage. Okay, using only one half of applied AC voltage means, so input to the rectifier is what? AC, isn't it? So you can see this waveform. So no need to select pen again and again, but I usually do that. So whatever it is. See here, this is our AC input to the rectifier. Okay, this is the input to the rectifier, which is alternating quantity. Okay, so what this rectifier does is, it only takes the half of the waveform. So you can see only half. Okay, so for positive half cycle, it has produced the output. For negative half cycle, it did not produce the output. For next positive half cycle, it has produced the output. Again for negative, it won't produce any output. Okay, so only for half of the cycle, it is producing the output. So if we are using a half wave rectifier, okay, this rectifier circuit which is shown here, which has only one diode. Okay, so you can see its input terminal of this diode is connected to a transformer, output is connected to some load, resistive load here. So if we are using a rectifier which has only one diode here, so what does it do? It will produce the DC voltage for half of the applied AC voltage. That's it. Okay, so if it is a full wave rectifier is this. This is the full wave rectifier. It uses both half cycles of the applied AC voltage and converts that into unidirectional pulsating DC voltage using both half waveforms of the applied AC voltage. That means, see here in this diagram, you can see, okay, you can see AC waveform. This is the input. Okay, for both half cycle, for positive half cycle, this is the output. For negative half cycle, for positive half cycle, again for negative half cycle. So for both half cycles, okay, of the input AC voltage, this full wave bridge rectifier is able to convert that into unidirectional pulsating DC voltage. So the output of the rectifier is, this is the output of the rectifier, which is, you can see, only in one direction. Output is available only in one direction, not in the negative cycle. Only positive cycle output waves we can see. Okay, so it converts applied AC voltage into unidirectional pulsating DC voltage. Okay, so what is our next block? Next block is, okay, where is it? Yeah, next block is, after rectifier, it is filter. Okay, next block is filter. You can call it as DC filter. Okay, you can call it as DC filter. So the rectified voltage from the rectifier. Okay, so the rectified voltage, what is the rectified voltage? This is it. This is the rectified voltage waveform from the rectifier with a pulsating DC voltage, which has high ripples, we can say. Okay, we can say the rectifier has high ripples. Okay, so when it is given as input to the filter, this filter will remove these ripples. Okay, and it will try to produce a smooth DC output waveform. Okay, so that can be shown. I have some diagrams here. So that can be done by connecting a capacitor to the given circuit, given rectifier bridge circuit. You can see here it's a rectifier bridge circuit earlier, which I have shown you here. So this is a capacitor which is connected actually across the load. This is our load. Across the load, so across the load, capacitor is connected parallel to the load. So what this capacitor will do is, whatever output that is produced by this bridge rectifier, it will smoothen the output of that voltage waveform, and it will produce a filtered output. So you can see here, you can see this is the output of your rectifier. Okay, this is the output of your rectifier. Okay, and this purple line, where is my cursor? This purple line, you can see this is the output of your filter. So when filter is connected to the output terminals of your bridge rectifier, okay, so you can see these dotted lines, you can see dotted waves or whatever is my cursor is here. So it gives out, this is the rectifier output, these dotted lines are the rectifier outputs, this purple line is the filtered output. Okay, one more diagram is there in the next slide. So this is it. This is the rectified output. These dotted lines are the rectified outputs, and this dark black line, this is our filtered outputs. Okay, so one more block is there. Last block in this block diagram. The last block is this regulator circuit. Okay, last block is the regulator circuit. Now if input changes, output should also change. Means this is our main input, isn't it? When this input change, what should happen? The output should also change. Okay, but what our aim is, even if we change the input, the output should not change. The output should remain same. So the output voltage or current, it will change or fluctuate whenever there is change in the input of your main supply. Okay, that changes we don't want. Okay, and we want output to remain constant. For that purpose, in order to maintain the output constant, we are using regulator. Okay, so this regulator, what does it do? It will maintain constant output even when there is any change in the input. So for that purpose, we can use transistors, bipolar junction transistor, isn't it? Along with the series regulators. Or we can use fixed and variable integrated circuit regulators. Or we can use even Zener diode operated in the Zener region. Okay. Or we can use integrated circuits like 78XX or 79XX to get the fixed voltage at the output. Or we can use, I have a circuit here. We have a circuit here. So, or we can use integrated circuit such as LM317. So you can see it is written here. There's my cursor here. This is LM317. This is an IC. IC means integrated circuit. So, or we can even use LM732. It is LM317. So these are the different types of integrated circuits. In detail about the integrated circuits is not required. That's why I'm not explaining just now for this topic. Okay, so they will produce, when they are connected in the circuit, they will produce a constant output. Okay, so even if input is changing, they will produce a constant output. So this is the circuit of the regulator. Okay, now let's go to the next topic, working of a full wave bridge rectifier. Just now we have seen before the filter, in the block diagram of regulated power supply, we have seen transformer is connected to the rectifier, isn't it? So the rectifier can be half wave rectifier or full wave rectifier. So today we will discuss working of full wave bridge rectifier. So you can see here, this is the circuit diagram of a full wave bridge rectifier. So what is the input to this full wave bridge rectifier? It is the AC input. Yeah, we have connected a transformer here for step up or step down, irrespective of. We can, depending on the requirement, we can either connect step up transformer or step down transformer to the rectifier. Okay, so what is the what is the input to this rectifier? Now V input is the sinusoidal input. Okay, V input is the sinusoidal input. I can show you the waveform. So this is the sinusoidal input. I have shown only one cycle here. Okay, so when sinusoidal input is given to this bridge rectifier, it will produce pulsating DC output. As I have discussed in the earlier topic, it will produce pulsating DC output. So see here, how many diodes are there in this bridge rectifier? D1, D2, D3, I'm sorry, D3 and D4. Okay, D3 and D4. Total 4 diodes are here. Okay, in this bridge rectifier, 4 diodes are connected in certain pattern. Okay, in certain pattern. If you observe carefully, I have erased here. If you observe carefully, this D1 and D3 are in similar direction, in same direction. D2 and D4 are in same direction. Okay, D1, D3 diodes are connected in one particular direction. D2, D4 diodes are connected in one particular direction, means in same direction. And this bridge circuit, in between terminal M, cursor, yeah, it is here. In between terminal M and L, load is connected. RL is the load. Okay, RL is the load. So whenever load is connected, that means that our aim is to fulfill the demand of the load. Okay, so what is input? AC supply is our input, sinusoidal input. Okay, sinusoidal input. And output, we expect, since it's a bridge rectifier, we expect pulsating DC output across the load. Pulsating DC output across the load. Now let us see how this bridge rectifier operates. So when supply is given, okay, AC supply is given during the positive half cycle. This is the positive half cycle. Okay, this is the positive half cycle of the supply. So for the positive half cycle of the AC voltage input, what will happen is the diodes D1 and D3 will conduct, whereas D2 and D4 do not conduct. Okay, during this positive half cycle, I have one more image here somewhere, and this is it. During the positive half cycle, this is positive half cycle, what is happening is D1, D3 will conduct, and D2 and D4 will not conduct. D2 and D4 will not conduct means they will act as open circuit. You can see here it is open. Okay, it is open wherever I have drawn the red circles. Huh? So it is open. Here it is open. So D2 and D4 are open. I'm sorry, I'm writing here open. Instead of writing open, I'm writing open. Okay, D2 and D4 will act as open switches. Open switch means current cannot flow. And D3 and D1 act as short circuit. They will act as short circuit. I am writing SC. Means short circuit. D1 and D3 act as short circuit. D2 and D4 act as open circuit. Therefore, current will flow. Okay, current will flow from this positive terminal to through this D3, through the load, through D1, and it will return back. I have one more image. See here, the current will flow like this from A. Current will flow from A through D1 to M, from M to L, and from L through D3, and it will return back to B. And from, of course, current has to, within the circuit, it will travel from B to A within the circuit, we can say. It's okay. So higher terminal to lower terminal. We should not write plus and minus for AC, but in order to understand the concept, it has been written here. That's it, nothing else. We should never write plus and minus across the transformer terminals. Okay, so this is the direction of current flow. So here, this is the direction of current flow. Okay, here D1 and D3 are conducting. Here I didn't even draw D2 and D4 here, you can see in this diagram. So D2 and D4 are acting as open switches, therefore current will not flow through them. Okay, so by looking at this diagram, what we can say is that these diodes D1 and D3, they are in series with RL during the positive half cycle. During what? During the positive half cycle. I am trying to draw. It has during the positive half cycle. During the positive half cycle, okay, D1 and D3 are in series to RL. Okay, and current is flowing through RL. Okay, so the current that is flowing through RL, yeah, where is it? This one. See, this is the input. The output current flow, because of the current flow through RL, the voltage across the RL is this. Okay, because of the current flow through RL, the voltage measured across the RL is this. This is the voltage. Now, after positive half cycle, what is there next? Negative half cycle. Okay, so during the negative half cycle of the input is sinusoidal, isn't it? Rectifier bridge input is sinusoidal in nature. So during the negative half cycle, what will happen is D2 and D4 will conduct, whereas D1 and D3 will act as open switches. Okay, D2 and D4 will conduct. So in this diagram, this is the flow direction of current flow. Okay, D1 and D3. Now, I'm sorry, I want to write something, but I'm writing something else. I'm habituated to write output and input. That's why even if I wanted to write open, I'm writing output. Okay, so D1 and D3, now they are acting as open switches, and D2 and D4 are short circuited. Okay, they act as short circuited or closed switches. Okay, D2 and D4 are short circuited, and D1 and D3 are open circuited. So yeah, this is the diagram. So you can see how the current flows. Okay, so this is the direction of flow of current. Current is flowing from B to D2 to M, M to L, L to L through D4 to A. Okay, this is the direction of flow of current. This is the direction of flow of current. Okay, this is the direction of flow of current. So the voltage and current flows through RL. The voltage that is measured across the RL, that voltage is, this is the voltage during negative half cycle, which is in the same direction. For AC, it was in the reverse direction for negative half cycle, but for rectifier, the voltage will be in the same direction. The second half voltage will be in the same direction of the previous half voltage waveform. Okay, so here current flowing through RL, okay, will be same as the previous half cycle. The current direction will not change. Okay, overall the current flow through the circuit may change. Direction of flow of current through the circuit may change. Okay, so the voltage that is appearing across the bridge rectifier will remain same. It will not change. So in order to understand this more clearly, you can see these waveforms. In these waveforms, cursor, yeah. So you can see this is our sinusoidal input waveform, input to the rectifier, bridge rectifier. So when during the positive half cycle, what will happen? D1 and D3 will conduct. Therefore, this is the output voltage across the load RL. Voltage across RL. During the negative half cycle also, when D2 and D4 are conducting, this is the voltage across the RL. During the positive half cycle, this is the voltage across the RL. During the negative half cycle, this is the voltage across the RL. So all the voltages are in same direction. So we can say DC output voltage is obtained, even though it is not purely DC, but okay, even though it is not purely DC, but we can say DC output voltage, pulsating DC voltage is obtained. So here D1, D3 is acting for positive, D2, D4 for negative, again D1 and D3 for next. D1 and D3 will conduct for this positive, for this negative, D2 and D4 will conduct. Okay. So you people, if you want, you can draw this diagram. I will give you a minute. You can draw the circuit. If you have completed, inform. As soon as you complete, inform. Okay, you can draw the waveforms also. These waveforms, you can draw it. Two more small topics are left over. As soon as I come, we will conclude as early as possible. There are small errors in these waveforms which I am rectifying. You can follow me. If you complete inform, make it fast, draw roughly. Okay then. So next topic is full wave bridge rectifier with capacitor filter. Just now we have seen full wave bridge rectifier. Now I'll discuss full wave bridge rectifier along with the capacitor filter. Just now you have drawn the waveforms also for the full wave bridge rectifier output waveforms. They were the pulsating DC output waveforms. So this is the schematic diagram for this full wave bridge rectifier. So here you can see this is our AC supply. AC supply. Okay, this is the transformer. Okay, and this is our bridge rectifier cursor. This is our bridge rectifier. This is our capacitive filter which is connected parallel to the load. Okay. So this bridge rectifier output is pulsating DC output. We already know that. So this DC voltage, this output DC voltage which is pulsating, it has lots of ripples. Means they are not purely DC. It is not a purely DC voltage. So it has lots of ripples that will increase to a maximum value and decrease to 0. That means the output of your rectifier, its voltage gradually increases, reaches a peak value or maximum value, and it becomes 0. Again it increases to maximum value and becomes 0. Again it increases to maximum value and becomes 0, and so on. That process repeats for each half cycle of your input. Where is my cursor? Yeah. For positive half cycle, this is the output of your rectifier. Negative half cycle, again positive. This is what we have already discussed in the previous topic. So okay, so there are lots of ripples in the DC output voltage waveform of your rectifier, which these ripple output DC voltages, they increase, they reach to their maximum value and they again decrease to 0. Again they will increase, reach to their maximum value, again they will decrease to 0. Okay, so we don't require this sort of output waveforms. Okay, these output waveform which we have seen just now, This sort of output we don't want. We want a pure DC output waveform. Okay. So we want a smooth DC output waveform. Okay. So what is DC output? How it should look like? It should look like this. This is it. If this is your time and this is your V out, if y-axis is V out, then this should be our pure DC output voltage. This is what we want. But by connecting a rectifier, we are getting the output with lots of ripples. Pulsating DC output is nothing but ripple output, we can say. So we want a smooth DC output voltage. So that can be obtained by what? By connecting a filter capacitor. Okay, so by connecting a filter, we can get a smooth output waveform. Okay, so this capacitor, which are in this diagram it is written C1. This capacitor is used as a filter, okay, and which is connected parallel to the load. Okay, so initially this capacitor is not charged, it is uncharged. Okay, this capacitor, initially this capacitor, it is not charged. Okay, during the first positive half cycle of your input, okay, during the positive half cycle, we know that during the positive half cycle, which diodes conduct? D1 and D3 will conduct. So when D1 and D3 are conducting, that means that D1 and D3 are forward biased. D1 and D3 will conduct during which cycle? During the positive half cycle. Okay, so we can say D1 and D3, they are forward biased. Okay, D1, D3 are forward biased. Okay, during the forward biased condition, when D1 and D3 are conducting, what will happen is capacitor will start to charge. C1 will start to charge. Okay, this capacitor charging will continue until this voltage reaches the peak value. Okay, the voltage, which voltage? Input voltage. So until this peak input voltage reaches peak value, okay, what will happen? The capacitor charge will go on increasing. As soon after reaching peak value, what will happen to the input voltage? It decreases, isn't it? It decreases after reaching the maximum value. So as the voltage decreases, capacitor will start to discharge. Okay. So at this point, what we can say is that input voltage will become equal to the capacitor voltage. At what point? When the input voltage is maximum, at this instant, when input voltage is maximum, V in is maximum. At that when V in, I can write in terms of equation, when V in is maximum, when V in is maximum, at that instant, capacitor voltage, let us assume Vc, capacitor voltage will be equal to the input voltage. Okay, when V in is maximum, capacitor voltage will become equal to the input voltage. So after reaching the peak value, okay, what will happen to the input voltage? It gradually start to decrease. Okay, at the same time, capacitor will start to discharge. So earlier when the voltage was increasing, okay, when the voltage was increasing, when the input voltage, when it was increasing gradually, when it was increasing, capacitor will also charge. Okay, the voltage across the capacitor will increase. When voltage starts to decrease, the capacitor starts to discharge. Okay, discharge through what? It will discharge through whatever it is, the charge that it has obtained. That charge will be discharged to the load. Okay, capacitor will start to discharge through the load which is connected parallel to the capacitor. Okay, okay, and what will happen? Current will start to flow through this load because of the discharge of this capacitor. Okay, until what? Until next peak occurs. Until next peak occurs. Okay, next peak is negative half cycle. Okay, so until this peak occurs, what will happen? Capacitor will start, the current starts to flow through the load, capacitor will be discharging. Once its value, then the current voltage value of this input again starts to increase, capacitor again starts to charge. Okay, it will charge until it reaches the maximum value. Okay, and as soon as it starts to decrease, I'm sorry, I have, instead of putting arrow mark on this side, negative, you see, even though it is negative cycle, I will erase all links, I will discuss once again. Even though this is a negative cycle, in the negative cycle, the voltage is increasing in the negative way. So minus Vp, I can say. Minus Vp is the negative peak. Okay, so once the voltage starts to increase, input voltage in the negative direction, reverse direction, once the voltage starts to increase, capacitor once again starts to charge. Okay, and once peak value is reached, what will happen? The input voltage will start to decrease. This is decreasing. When voltage is decreasing across the input voltage is decreasing, capacitor will start to discharge. So current starts to flow through the load. Okay, current starts to flow through the load when capacitor is discharging, because the capacitor is connected parallel to the load. Okay, so for a negative, this is for the negative half cycle. One more thing, during negative half cycle, which diodes are forward biased? D2 and D4 are forward biased. During the positive half cycle, D1 and D3 are forward biased. Okay, so and this process continues. Okay, this process will be repeated again and again, and the voltage that is obtained across the capacitor will be uh, ripple free voltage. Even though it may see, if you see here, it is not even purely DC voltage, but it's better, far better than the previous rectifier output voltage. So what is happening here? This capacitor, okay, this capacitor, this capacitor will charge. Okay, when the voltage, input voltage gradually increases and reaches the maximum value. Okay, and once the current or the voltage of the input starts to decrease, capacitor will start to discharge. So whatever charge that is accumulated in the capacitor, that charge will be discharged to the load, and the current start to flow through the load. Okay, that is for one cycle. For the negative half cycle, again capacitor will be charged. Okay, gradually the charge across the capacitor will increase. Once peak is reached, capacitor voltage will become equal to the peak voltage of your supply. And once input voltage starts to decrease, capacitor will start to discharge, and charge will start to flow through the load, and load current will flow through the uh, current will flow through the load. Okay, and this process continues for each half cycle, and the output voltage that is obtained, it is ripple free. Of course it is not smooth waveform, but it is ripple free. So DC output waveform with capacitor filter. DC output waveform with capacitor filter. This dark red line is the DC output waveform. So if you want, you can draw this diagram. So one more small topic is left over. As soon as you complete this, inform, so that we can go to the next topic. If you have already drawn it, it's okay. You can mention already completed. You just mention in the chat box you have already drawn it in your notes. Okay, completed. Then you can even draw these waveforms, AC input voltage waveform and the capacitor DC output voltage. This DC output means this is not the voltage across the capacitor, it is the voltage across the resistor RL. V out means voltage across the resistor, resistive load. Okay, whatever load that you connect. Did you complete the waveforms also? You just mentioned. Did you complete the waveforms? You just mentioned W in the chat box so that I will come to know that you have completed. One more small topic. I will discuss about it briefly and we will conclude. Okay. So I hope everyone have completed. Now let us go for the next topic. Where is it? Next one, last one. Last topic for this session is Zener diode as voltage regulator. I'm sorry, here spelling mistake is there. Zener diode as voltage regulator. Okay, so this is the schematic diagram when Zener diode is used as voltage regulator. So you can see this is our input voltage V in, and there is a resistor, some RS series resistor connected to the source, and you can see this is our Zener diode. Okay, and this is the current that is entering the Zener diode IZ, and this is the voltage across the Zener diode, and this is our resistive load RL, load connected across the Zener diode. So our topic is what? Zener diode acting as an voltage regulator. Here, what is meant by voltage regulation? Voltage regulation means if any device is acting as a voltage regulator, it should be able to provide a constant output voltage to the load. Okay, which is connected parallel to that particular device, irrespective of how energy varies in that particular load, or irrespective of supply voltage is constant or not. Okay, so whether it is an unstable supply, whether the load is constant or not, irrespective of that. Okay, so means load is constant means the energy drawn by the load is constant or not, irrespective of that, the voltage regulator must be able to provide constant output, okay, to the load. So here we are using a Zener diode. We are using a Zener diode which will provide constant output voltage here, uh, provided that current stays within the limits of maximum and minimum ranges. So current should not exceed certain limit on the maximum side, or it should not decrease to very low value. Okay, so the current that is supplied to this Zener diode IZ, okay, so it should be even if it is varying, okay, it can vary. This IZ, it may vary if the supply input is varying, it may vary. Okay, the IZ may vary, but it should have certain limit. Okay, maximum, certain range, maximum and minimum, within certain range of some maximum and minimum range. Within this range, If this IZ is available, then Zener diode can act as a voltage regulator, okay, and it will provide constant voltage to the load. So here, if you see in this diagram, this RS is the series resistor that is connected to the source, okay. The aim of this resistor is to limit the amount of current flowing through this diode, okay. In order to limit the current flowing through this Zener diode, this RS is connected. That's the main purpose of this RS. And you can see input voltage Vin. It should be always greater than the VZ, voltage across the Zener diode. So initially, V input should be always greater than the Zener voltage, input voltage. Okay. And whatever voltage that you measure across the load, this is our load, isn't it? The voltage that is measured across the load, let us assume output voltage V out. Okay, V out. The V out should be always equal to the Zener diode voltage, that is VZ. V out should be equal to VZ. Okay, and we already know that Zener diode always operates in the reverse bias mode. Okay, so these reverse bias mode characteristics of the Zener diode, they are used to regulate the voltage and to produce a constant voltage. Okay, so the voltage characteristics are not, I have not drawn any voltage characteristics here. Okay, so simply when input is given, the input current will be limited by this series resistor. Okay, and whatever current flows through this diode, because voltage will appear across this Zener diode, this voltage will be equal to the output voltage. Okay, when the Zener diode operates in the reverse bias mode, okay, constant output voltage is obtained, which will be purely DC in nature. Okay, so this is time and this is V out. So this V out will be always purely DC in nature. That's it. Okay. So here purpose of Zener diode is what? Even though input varies, okay, even though the energy through this load varies, the output should remain constant. That's what this Zener diode do. Okay, that's it. Our session is over. Okay, I forgot to ask you to draw that. You can draw this circuit. If as soon as you complete inform, we will conclude. We can even connect a capacitor across this Zener diode to smoothen the output waveform, but we have not connected here in this diagram. Okay, that capacitor you can call it as decoupling capacitor. You can connect it, but here we didn't show it in the diagram. Did you complete? Anyhow, I will conclude. You can draw the diagram later, isn't it? You can draw the diagram later. I will conclude. this session.